Full voltage starter calculations. In this presentation, we're going to be looking at how we determine the following items: the FLA of a motor, the inrush current of the motor at start, the full load torque, the starting torque, the current on the line and load side of the starter, the voltage on the line and load side of the starter, and finally, the overload size in the motor starter. Well, first thing we need to know is what type of motor we're dealing with. The motor we're going to be working with is a skim motor, 600 volt, 3-phase, 9-lead dual voltage, 25 horse, service factor of 1.15, 1760 RPM, kVA code F, and a starting torque equal to 300% of the full load torque value. Now, the first place we're going to start is the FLA because most things are based on this value of current. The FLA is going to be found in table 44 of the CEC, and you'll notice in the table that the voltage columns that are shown do not line up precisely with the nominal system voltage that we typically reference. Motor manufacturers often, if not always, rate their motors to a slightly lesser voltage value, and this is simply guaranteeing the ratings at the voltage given. So we look at the 575 volt column for a 600 volt motor, and we find an FLA value based on 25 horse of 27 amps. The next item we're going to look at is the inrush current. The inrush current is based on the kVA code, in this case, kVA code F. F in the NEMA table represents 5.6 kVA per horsepower. If we then take this value and multiply it out, we end up with a total of 140,000 VA that's required for the motor at start. After doing a basic three-phase calculation for line current value, we come out with a total inrush line current of 134.71 amps. Now, the next item we're going to look at is the full load torque value. Now, full load torque can be calculated for metric or imperial. For this process, we're only going to be using the imperial method. The full load torque value is based on the horsepower times 5252 divided by the RPM at full load, which then leads us to 74.6 foot-pounds worth of torque. The next item we're going to look at is the starting torque, and the starting torque is actually a very basic calculation based on the percentage given in the question. These are general numbers and general percentages that are usually based on the design of the rotor of that specific motor. So for our installation, we have the full load torque times the percent, and the percent given in the question was 300%, so 223.8 foot-pounds of torque would be available at start. The next items we're going to look at are the current and voltage on the line and load sides of the starter, and finally the overload size itself. Now it seems like a little bit of a foregone conclusion that they are going to be identical on a full voltage starter, and yes, certainly they will be. However, this will change as we start looking at different types of starters. So for the current, we're looking at start, same value of current on both the line and the load side of the starter. And even when we're discussing the run, well, 27 amps and 27 amps would be present on the line and load side of the starter. So it'd be identical. The voltage for this particular motor would be 600 volts. It's a 600 volt system, so the line value voltage would be 600 volts between T1, T2, or T2, T3, so on and so forth. And finally, the overload size. Now, the overload size is based on a rule in 28306 subrule 1, and we need to know what the service factor is. So take a reference to that rule in your codebook, and then we will go through the process. So the overload size is dependent on the service factor. And when we read in 28306 subrule 1, it is based on the service factor being 1.15 or greater for one multiplier or less than 1.15 for another multiplier. Now the FLA for the motor is then multiplied by 28306, or the value rather, that's given, and we get our max overload from this. In our situation, we have 27 amp FLA times 1.25 multiplier, which is given in the rule, for a maximum size overload of 33.75 amps.